Stan Gibilisco here, proprietor and operator of amateur radio station W1, GV, Whiskey 1, Good Vibrations. Here to describe one of the largest, most important advantages of circular polarization when it comes to propagating radio waves by means of the ionosphere. This is familiar to most radio hams. Severe fading that occurs with ionospheric propagation. Here I think it should be pretty obvious what these lines represent. This is the ionospheric F layer. F is in Frank, the surface of the Earth, a vertical antenna, and a dipole antenna. Although these could be any linearly polarized antennas whatsoever. They could both be vertical, they could both be dipoles, they could both be slanted, they could both be loops, anything at all, so long as this antenna transmits a linearly polarized wave, and this antenna is intended to receive another linearly polarized wave. When that happens, we get a problem. With the line of sight or direct wave, no problem. The antennas align, you get the best results. They don't align, you get progressively poorer and poorer transfer of signals. But when a signal encounters the ionosphere and it has linear polarization, the ionosphere tends to screw up the orientation of the lines of electric flux, so that you end up with what you might call chaotic linear polarization on the way back down. And it doesn't matter what kind of antenna you're using, if it has linear polarization, you're not going to get the best possible results. You're going to experience some fading when the strongest signal coincides with alignment of the polarization with the antenna, and the worst reception coincides with 90-degree angle between the orientation of the electric lines of flux in your antenna. And that can't be predicted. It's a chaotic, almost random fluctuation, most noticeable by means of polar propagation under exceptional circumstances, auroral propagation, or just in general propagation when the ionosphere is not terribly well established. But you're always going to hear this QSB, the bane of one of the banes of the amateur radio operator's existence. Of course, now increasingly we're getting QRN and QRM from home appliances, which may someday surpass all other forms of interference in terms of severity and destructiveness to ham radio communications, unless our engineering ingenuity gets us a way to overcome that, and I'm convinced that it will. But there's another way to overcome this. Use a circularly polarized antenna at one end of the circuit at least, because a circularly polarized wave, which causes rotation of the electric lines of flux, is harder to discombobulate and disorient than is a linearly polarized wave, because, to a certain extent, the circularly polarized wave is already disoriented. It already has a poorly defined direction or orientation of the electric lines of flux. So when they come back down, particularly if this receiving antenna is intended for circular polarization, it doesn't matter what direction the electric lines of flux happen to be oriented. If it's a circularly polarized antenna, you're going to get excellent results no matter what. Not the very best possible, but passable. I'm not going to make a loop antenna here because that would mislead you. Circularly polarized, I'll make a spiral of Archimedes for your antenna. This, in particular, is the best arrangement and one of the great advantages of circular polarization, particularly when receiving signals from the ionosphere. It doesn't matter how the electric lines of flux may happen to orient themselves. the circularly polarized antenna will always get some of it, and it'll always get pretty much the same amount, so you will have a lot less QSB. Try it sometime and see for yourself. But in some other video, I'll have to show you how to build an antenna that will get you circular polarization if you don't already know. Stan Jabalisco W1GV saying 73, which means best regards, and so long, which means, in my native fist, da-da-da-da-da-da.